Okay, so we are back with the second video. Hopefully the first one you got through it and you were okay. Now let's actually get into the heart of working through these problems. So example 4 is find the RLC and the LLC for this series here. Okay, so again we're going to use the ratio test, and so I said that more often you're just going to use the ratio test if everything. So that 3 needed to also be raised to the n in order for you to say, oh, the root test would be better. Okay, but we're going to use the ratio test for here. So I'm going to go over this problem more in detail because we're just starting off, but the other ones I'm going to have you sort of work through the algebra yourself and just sort of give you sort of simplified answers. Although I'll show my steps, I'm just going to sort of have it all on the screen. But here I want to go over it with you in detail. Okay, so recall the ratio test formula. So here we have the ratio test formula with rho is equal to the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. Okay, and so we are going to use that to determine our interval of convergence and our radius of convergence. Okay, so we are here. I'm going to put it all together. You can separate it, and sometimes it's easier to do like we did with the regular ratio test. Just do your a sub n plus 1 over a sub n first. Here, it's not going to be too bad, so we're just going to sort of put it in together. So rho is equal to the limit as n goes to infinity of the absolute value of 3 times x minus 5 to the n plus 1, right? All over 3 times x minus 5 to the n. All right, and so this equals, and yeah, I probably would simplify it first because we're going to have to keep writing our absolute values. But so I'll do this one and probably the next one step by step with you, and then the other ones I'll have you sort of kind of do your own. Okay, so again, this is equal, and I'm going to break this down. This will be the limit as n goes to infinity. Excuse me, my voice is going in and out, but of the absolute value of 3 times x minus 5, we can break that up, right? So it'll be x minus 5 to the n times x minus 5 all over 3 times x minus 5 to the n, okay? And you should see that we have something factoring off, and so that's going to leave us with, I don't know if I'm going to have space, so I'm going to continue here, the limit as n goes to infinity of the absolute value of 3 times x minus 5 over 3, right? Actually, that simplifies too, so we could just factor off those 3's, and so we'll just be left with the absolute value of x minus 5, right? So I don't have to make that bar that long. Okay. Now, and now we can even drop the limit, because so we really can drop the limit. I'll go back. Once you're done evaluating n, or if there's no more n's left, because the limit only refers to the n variable, not the x. It's independent of the x. So this just equals, and so this is a great handy dandy eraser I have here. The absolute value of x minus 5. So that's what rho equals. Now we know from the ratio test that we just did in class that this will converge absolutely when what happens? Well, when this absolute value of x minus 5 is less than 1. Okay, so excuse me, what that's saying in this format, and if you recall, if you go back to the first your first set of notes or the first video, this form here, we actually will be given our c and our, well, actually you can see your c from the beginning of the problem, but our r is now seen here, as long as, and we'll get to an example where it won't be the case, but keep in mind this will always be, so this is your ROC, as long as this variable here, there's no constant in front of it. The only coefficient is 1. If there's a coefficient other than 1, you have to factor that coefficient out, and your ROC could change. So don't assume that your ROC will always be 1. It really depends, and we'll see some examples. But in this example, our ROC is 1. So to figure out our interval of convergence, right, we just take, so we have the absolute value of x minus 5 is less than 1. by definition of absolute value, that means -1 is less than x minus 5 is less than 1. If we add both sides, 5 to everything, we get 4. X is between 4 and 6. So this is our interval of convergence. However, but wait, we have to check endpoints. All right, so we need to check endpoints. And why do we need to check endpoints? Good question you ask. We need to check endpoints because if you recall for the ratio and the root test, if you equal 1, then the test is inconclusive. And so what that signifies, or what that represents in your interval of convergence, is it represents those endpoints. So you don't know, one or more or none could converge or diverge. So you have to check your endpoints. You always need, when you're doing a power series and you're finding the interval of convergence for a power series, you always need to check your endpoints to see if you're going to include your endpoints or not. But checking it is not going to be too bad. We're about to check it in 1 minute. But just keep in mind, you always need to check your endpoints. So do not stop. So in essence, this is really sort of what I would like to call maybe your possible IOC, although they don't phrase it like that, but it's sort of your possible IOC because it could differ just according to the endpoints could differ, right? Anything in between those endpoints will be there no matter what. But until you check your endpoints, you don't know if this is all of the points that will converge on that particular power series. Okay, so I had to go to a new slide, but to check your endpoints, you go back to your original power series and you just plug in and you evaluate. So recall our sort of possible, although we know it's our interval of convergence, we need to check. So it's not really our possible, it is our interval of convergence, it's just without checking endpoints, so we need to check endpoints. So that's why I call it possible, but it really is your interval of convergence. You just have to make sure you check those endpoints. So you need to evaluate f of 4 and f of 6. So similar to what we did in example 3. Okay, so for f of 4, we're going to get, so this is the series, n goes from 0 to infinity, 3 times 4 minus 5 to the n, and that's going to be the absolute value of n equals 0 to infinity, and that's 3 times -1 to the n. And so now you guys have graduated, congratulations, and moved up in regards to showing what test is going to make this diverge. Well, you have to state it, but you don't have to do any additional work. So you don't have to do any additional work. You just have to state how it converges, okay? And so here, and it could be different ways you can show whether it converges or diverges. Here, one way in this first, looking at this first series, notice that this is going to fail the divergence test, right? Because if you take the limit as n goes to infinity, it's not going to equal 0. So you can say this diverges by divergence test or nth term test. I'll say nth term test. And you're done. It's also a geometric series that diverges because r is equal to the absolute value of r is 1. So you could also say diverges by geometric series, but you don't have to prove anything else. You don't have to state how it diverges. As long as you tell me which test you're using, that's it. So congratulations on graduating to that. Now for f of 6, let's evaluate it the same way. And notice I didn't have to string out any terms, right? You just simplify what's in the power series and you should be able to see what happens, whether it's going to converge or diverge. All right, and so this one will become 3 times 1 to the n, and this also diverges. And I'll switch it up and say diverges by geometric series. Okay. Or you could have kept divergence test, but I just wanted to show you that you can switch it up. Whichever test, it could be multiple tests that diverge, just state one of those tests. Be clear on it. You don't have to show any work. So if you say it diverges by AST or converges by AST, you don't have to show that those 3 properties are true. I can look at it and determine it, but just make sure you're not haphazardly using the test without being sure. So just be careful there. So more than likely you'll look at like geometric series and term tests. You could possibly do an AST. You could possibly say integral test if you clearly see. Just make sure you clearly see, or P series or whatever. Just make sure you clearly see what the test is. You don't have to prove it, but just make sure you clearly see what the test is going to be. So therefore, we can say thus our IOC is going to be 4.6. We keep, remember, just recall, open parentheses here means that you don't include the endpoints. If you did include the endpoint, then you would use the bracket symbols. Okay, so just keep that in mind. So the IOC is 4 to 6, and then the ROC is 1. Okay, so I think, again, I'm going to do this example with you all just to make sure you're clear. And then the remaining examples, I'll just sort of give you the brief version until we get to number 8, which is a little different. All right, so find the IOC for this. So this one here, I will break up. I'm not going to do like the last one and just keep writing the limit and the absolute value. I'm going to break up because we have to do some simplification. So I'm going to do it similar to how, and this is how you really can do all of them, is first start off by simplifying the ratio. So that's going to be x to the n plus 1, right, over the square root of n plus 1 times 6 to the n plus 1, and that's all over x to the n over square root n times 6 to the n, and that equals x to the n plus 1 all over the square root of n plus 1 times 6 to the n plus 1 times the square root, flip the denominator, square root of n times 6 to the n over x to the n, okay? And that simplifies, again, properties of exponents. The top will be, and it's going to be all multiplication, so we can bring it all on one line. X to the n times x times the square root of n times 6 to the n. And then in the denominator, square root of n plus 1 times 6 to the n times 6 times x to the n. All right, and so let's see what factors off. We have our 6 to the n's will factor off, our x to the n's will factor off, and we will be left with in the numerator, I'm going to bring that square root of n out front, square root of n times x all over square root of n plus 1 times 6. Okay, and so this is as far as we can go now. And now, so we know that rho is equal to the limit as n goes to infinity of the absolute value of the square root of n times x over the square root of n plus 1 times 6. Here, so remember when I talked in class about the absolute values, you do have to be careful here in regards to x, because your x could possibly be a negative number, right? So, but everything else we can take out because n is starting from, I really should have had that starting from 1. Did I have it starting from 1? We can make that starting from 1. All right, so we make that starting from 1. So n is starting from 1 to infinity. So n is always going to be positive. So we can take the n and we can take the 6 out of the absolute value, but we have to keep the x in the absolute value because x could possibly be a negative number. So this is going to be the limit as n goes to infinity of the square root of n over the square root of n plus 1. Actually, let me rewrite this. I want to put that 6 in the front. So it's the square root of n over 6 times the square root of n plus 1, and then times the square root of the absolute value of x, okay? And again, you guys have graduated past having to force factor and do all that. You don't have to do that here. As long as you know, if you need to force factor, you should force factor, okay? But here, you can't use limit laws because it's not; these aren't polynomials. But you can force factor. But you should see that once you force factor, you're going to get the limit here is going to be 1/6, and now we can drop the limit because x is independent of n. They're not connected. So once you've evaluated everything involving your n, you can now drop your limit. So this is going to equal 1/6 times the absolute value of x. And now we know, so we know that 1/6 times the absolute value of x will converge absolutely when that is less than 1, right? We know that by the definition of our ratio test, right, and how we set it up. Okay. However, so this is an example where you need to multiply. So if you multiply 6 on both sides, we get the absolute value of x is less than 6. So now this is your ROC. Okay, so your radius is 6, right? And then, so that means you have negative 6 is less than x is 6. And this becomes your IOC. But don't forget to do what? We have to do what? Exactly. Check endpoints. All right, so we have to check endpoints, which I'm going to do on the next slide. Okay, so we're over the 15 minutes, but I think I can get this done hopefully in the next 2 minutes. So when x is equal to negative 6, right? So if we substitute this in, I want to be careful. I want to show you this. So let's do this. I'm sorry. So f of negative 6 will equal negative 6 to the n over the square root of n times 6 to the n. And now you have to think about properties of exponents. We can rewrite this as, and I'm going to do it in 2 steps, although you really can do it in 1. We can rewrite this as 1 over the square root of n times negative 6 over 6 to the n, right? Well, that just simplifies. So that simplifies to n goes from 0 to infinity to negative 1 to the n over the square root of n, right? And so that's what that simplifies to. So now this actually, you might have to think about it for a minute, but this will converge by the alternating series test, which I call AST. So this will converge by the AST. That means we need to include negative 6 in our interval of conversions. Let's try it for positive 6. Okay, so when you evaluate it as 6, then this is what your setup will look like. And after you simplify it, you get 1 to the n, which is just 1, right? So you get the series 1 over the square root of n. And n goes from, I think I changed it to 1. So you can change that to 1, but that's fine. That's irrelevant here. So this will diverge by p-series. Okay, so don't assume if one endpoint converges and the other one has to. In this case, you see it's not. So it converges at negative 6, but it diverges at 6. So our conclusion will be, therefore, the IOC equals, when you include, you add brackets. So it's negative 6, bracket negative 6 to 6 parentheses. All right, and so I'm over my time of 15 minutes, but so it will be 3 videos. I will really try to stop at 3 videos, but I want to make sure you get this. So make sure you go back over it, and hopefully you understand. I'm just going through these ones thoroughly with you. The next ones, I'm going to speed through them. All right.